Hello everyone, this is lecture 13 of the subject analog circuits. In this class, I am going to discuss cascode amplifier, general feedback structure and properties of negative feedback. So, starting with the cascode amplifier, firstly let us understand that what is the difference between cascade and cascode. Do not be confused between cascade and cascode, both are different. In cascade structure, what we do, we connect more than one amplifier in cascade. So, this is your input signal V in, this is your amplifier 1 and the gain of voltage gain of the amplifier 1 is AV1 and the output of the first stage is connected to the input of the second stage and the voltage gain of the second stage is AV2, this is your V0. This is your cascade structure, this is also called 2 stage amplifier. So, we can design 3 stage amplifier, 4 stage amplifier, n stage amplifier and the gain of this overall structure, it is multiplication of the voltage gain of the individual stages. So, cascade, we do the cascading of the amplifier stages to increase the gain. This is about the cascade, this is your called multi-stage amplifier, fine. But in cascode what happens, we use two configuration, we combine two configurations of the transistors, whether it is BJT or MOSFET. While using MOSFET, we combine common source amplifier and common gate amplifier. The advantage of the cascode amplifier is it combines the advantages of CS amplifier and CG amplifier. The advantage of CS amplifier is its input resistance is high, higher transconductance, but the issue with the common source amplifier is it is having Miller effect, due to that bandwidth is reduced. But the advantage of common gate is, firstly it is having current buffering property, that is one part, and the another important part is that CG common gate, it is not having any Miller effect, because of that the high frequency response of CG is better. So, basically the cascode amplifier, it combines the advantages of CS and CG. So, you can see that in CS amplifier we apply the input at the gate of the transistor, we take the output from the drain. Now, the output of the CS is connected to the input of the common gate. In common gate we apply the input at the source terminal and we take the output from the drain terminal. So, you can see that input is applied at the gate of Q1 transistor, that is in CS configuration, and Q2 is in CG configuration. And what is the role of this VG2? VG2 is the bias voltage and this I is the bias current, and the value of VG2, it should be such that both the transistors Q1 and Q2, it should be in saturation region. So, this is the cascode amplifier using MOSFET. Similarly, we can design cascode amplifier using BJT. In BJT, what we do? We take common emitter amplifier and common base amplifier, fine, and there we need to ensure that in BJT both the transistors should be inactive, but in MOSFET both the transistors Q1 and Q2, it should be in saturation region, fine. So, the basic idea behind the cascode amplifier is to combine the high input resistance and large transconductance in CS amplifier with the current buffering property and the superior high frequency response of the CG, that I have explained that. So, we are combining the advantages of CS and CG amplifier in cascode amplifier. Cascode means common source plus common gate while using MOSFET. While using BJT, it will be common emitter plus common base. So, advantage of cascode is it is used to obtain wider bandwidth while equal DC gain as compared to CS amplifier. So, the main advantage is the bandwidth is enhanced, because in CS amplifier the issue is that you have seen that in the last class, due to Miller effect the input capacitance, equivalent input capacitance is increased, because of that bandwidth is reduced. So, to combat that bandwidth issue in CS amplifier, we use this cascode amplifier. So, you can see that this is another application of CG, although when we design voltage amplifier, then we do not use common gate amplifier individually because of its lower input resistance, but The beauty of the common gate is that it can be combined with common source in order to enhance the overall performance of the bandwidth. That overall performance is your bandwidth. The bandwidth is enhanced in cascode amplifier. That's all about cascode amplifier. Next is feedback. So, feedback is, we all know that this is your open loop amplifier, there is no feedback. Now, if the output is mixed with input, then we say that there is a feedback. Now, this output is mixed with input in two forms, it can be added or it can be subtracted. When your output is subtracted from input, that is called negative feedback. If it is added, that is called positive feedback. So, there are two kinds of feedback. One is negative feedback and another one is positive feedback. This negative feedback it is used in amplifiers, and the positive feedback it is used in oscillators. So, in unit 2 we are going to study about negative feedback. In unit 3 we will study positive feedback. In unit 3 we will study oscillators. In oscillators positive feedback is used, fine. So, in negative feedback, when we use negative feedback, then what happens? So, one example of negative feedback I had explained in biasing in unit 1. There we have used a resistance Re at the emitter terminal and resistance Rs at the source terminal of MOSFET, and the function of that Re and Rs in BJT and MOSFET amplifiers is it provides negative feedback, and the advantage is that since it provides negative feedback, because of it the bias current do not change, the bias current is stabilized. That is the function of negative feedback. This is one application that we have already learned in unit 1. Now, we will study this negative feedback in detail. What are the advantages of negative feedback, what are the different properties, is there any limitation of negative feedback, etc. And this negative feedback is very important because it is used in amplifiers, and in analog design mostly part is covered by amplifiers. So, coming to the properties of negative feedback, the first property is it desensitize the gain. Desensitize the gain means it make the value of the gain less sensitive to the variation in the value of the circuit components that may be caused because of the change in temperature. So, the point is that if there is a change in temperature, then what we want? Because of the slight change in temperature, we want that our gain, our voltage gain of the amplifier, it should not be sensitive to the variations in the circuit component, in the value of the circuit components, because if there is a slight change in temperature, if there is a slight change in circuit components, then our gain it should be insensitive to that change. That should happen, that we desire, and it can be achieved with the help of negative feedback. Second property is it reduces the nonlinear distortion. That is another important thing. In amplifiers, what we want? We want linear amplification. We do not want any distortion, because if at the output of the amplifier we are getting distortion, it means that the shape of the amplified output signal it is changing. If the shape is changing, it means that information may be lost. So, we do not want any distortion at the output of the amplifier. So, this negative feedback it reduces the nonlinear distortion, that is very important. It also reduces the effect of noise. Obviously, we do not want noise, but in analog circuits there will be noise, fine. So, what we can do? We can reduce that noise, we can minimize that noise, and with the help of negative feedback we can reduce the effect of noise. We will derive these things also, we will understand in detail that how negative feedback it desensitize the gain, it reduces the nonlinear distortion, it reduces the effect of noise. We will see it thoroughly. Next is negative feedback, it can control the input and output resistance. That is very important, because for different amplifiers the input and output resistance required it can be different. For voltage amplifier it is different, for current amplifier it is different, fine. So, with the help of negative feedback we can control the input and output resistance. Next is obviously we want more bandwidth. This negative feedback it extends the bandwidth of the amplifier. So, these are the properties of negative feedback. You can also say that these are the advantages of the negative feedback. These all are the advantages of negative feedback, but we get these advantages at the expense of the reduction in the gain. The drawback of the negative feedback is it reduces the gain, that is the drawback. Otherwise, there are 5 advantages. So, there is a trade off, So, as I discussed that all the desirable properties it can be obtained at the expense of reduction in gain. So, the basic idea of negative feedback is to trade off gain for other desirable properties. So, what we have to do, we need to specify that how much gain we want from the amplifier, and to achieve that gain then we set other parameters, fine. But obviously, the gain is reduced, but we have to be specific that how much gain we require. And this application of negative feedback I have already discussed that ammeter resistance that stabilizes the bias point of the bipolar transistor. Also this negative feedback it increases the input resistance. I had discussed in unit 1 in the common emitter amplifier in the derivation part that with the help of this RE resistor the input resistance is enhanced, and now we will see that how the bandwidth is improved with the help of negative feedback, how the linearity is improved with the help of negative feedback in this class, fine. So, next is general feedback structure. This is the general feedback structure of the negative feedback. For positive feedback, just what happens, this negative sign will be replaced with the help of positive sign. So, here I am not going to discuss the positive feedback. In unit 3 I will discuss it in oscillators part, what is positive feedback, what is the need of positive feedback, fine. So, you can see that this source is generating some signal XS, and this is amplifier, basic amplifier, and the amplifier, the gain of that amplifier is A, and the input of this amplifier is Xi and the output is X naught. Now, this X naught it goes to the input side through this feedback circuit, and the gain of that feedback circuit is beta. This beta is called feedback factor or feedback ratio. This beta is called feedback factor or feedback ratio, fine. This is a load across which we get the output. Now, see what is happening here. The output of this feedback circuit is Xf. This Xf it goes to this mixer. Now, this Xi is generated. What is the value of Xi? It is Xs minus Xf. You can see that Xs minus Xf because of the negative feedback. And what is the value of X naught? X naught is A into Xi because the gain of the amplifier is A. Now, try to understand that what is this A? This A is open loop gain. This A is open loop gain. Open loop gain means gain without feedback. Open loop gain means gain without feedback. So, X naught will be A into Xi, simple. And what is Xf? Xf will be beta into X naught because X naught is coming at the input of the feedback circuit. So, what will be the output of this feedback circuit? It will be beta multiplied by X naught. Now, just rearrange these 3 equations. From here you can get the value of X naught upon Xs. What is this X naught upon Xs? This X naught upon Xs is the gain of this complete amplifier. Complete amplifier means now when we are using this feedback, it means that now this amplifier is called closed loop amplifier. Closed loop amplifier means amplifier with feedback. So, it will be X naught upon Xs. We can calculate it X naught upon Xs. Just what we have to do, just to put the value of Xf here. Now, just put the value of Xi here, just rearrange the terms. We can calculate the value of X naught upon Xs, that is A upon 1 plus A beta. Now, try to understand what is AF. What is AF? AF is your closed loop gain. AF is closed loop gain. Closed loop gain means gain with feedback. A is open loop gain, that means gain without feedback, fine. Now, you can see that the closed loop gain which we are getting, that is equal to A upon 1 plus A beta. Now, you can see that without feedback the gain is A, but when we are using the negative feedback, then your gain is reduced by the factor 1 plus A beta. So, that is the issue with the negative feedback, the gain is reduced by the factor 1 plus A beta, and this 1 plus A beta factor, it is called amount of feedback. A beta is called loop gain. So, again I am mentioning these points. A is your open loop gain, AF is called a closed loop gain, beta is your feedback factor or feedback ratio, A beta is the loop gain, and 1 plus A beta is the amount of feedback. So, these are very important terms, fine. Now, if your A beta it is very greater than 1, then what happens? Since AF is equal to A upon 1 plus A beta, and if A beta is very greater than 1, then we can write closed loop gain as A upon A beta, A cancel out, then it will be approximately equal to 1 by beta. So, the point is that when the loop gain is large, then your closed loop gain will be 1 by beta, that is important thing. It means that when your loop gain is high, then your closed loop gain is independent of the gain of your basic amplifier, that is an important result. Now, it means that just by varying the feedback factor, we can change the overall gain, that is your closed loop gain, fine. And another important thing is that now the feedback factor is deciding the overall gain. Now, if we design the feedback network carefully, then we will get the accurate gain, predictable gain, and of course, the stable gain. That is the advantage. So, the first property that I have mentioned, that is the gain desensitivity. So, in the gain desensitivity, how we calculate it? Since we have already get the expression AF is equal to A upon 1 plus A beta. Now, if we differentiate this AF with respect to A, now we can differentiate it, and after differentiating we will get DAF is equal to DA upon 1 plus A beta square. Now, just divide by the factor AF, then we will get this expression. Now, just observe this expression, you can see that DAF upon AF is equal to 1 upon 1 plus A beta into DA by A. So, the point is that the percentage change in AF due to the variation in some circuit parameter is smaller than the percentage change in A, because see the percentage change in A is DA by A. Corresponding to this, the percentage change in AF, it is reduced by the factor 1 plus A beta, 1 upon 1 plus A beta, that is the good thing. Now, your variation in closed loop gain, it is lesser in comparison with open loop gain, fine. A is your open loop gain, that is gain without feedback, AF is your closed loop gain, that is gain with feedback. So, with the help of negative feedback, your variation in gain is lesser by which amount? By the amount 1 plus A beta, that is a good thing. We want a stable gain, we do not want that our gain should change if there is a small change in the parameter values, if there is a small change in temperature, we want stable gain. So, this is the derivation part to understand that how this negative feedback, it is desensitize the gain. Now, next is bandwidth extension. Negative feedback, it extends the bandwidth. To understand it, now see your AS, that is the gain without feedback, AM upon 1 plus S upon omega h. This thing I had discussed in the last class, there we have derived this expression AM upon 1 plus S upon omega h. Omega h is your upper 3 dB frequency, AM is your midband gain. This AS is the gain without feedback. Now, what is the gain with feedback? It is AS upon 1 plus beta AS. Now, just put the value of AS in this expression and rearrange the terms, we will get this. Now, you can see that this is the expression AFS, that is AM upon 1 plus AM beta upon 1 plus S upon omega h into 1 plus AM beta. from this expression you can see that your mid band gain, it is reduced by the factor 1 plus AM beta, and your upper 3 dB frequency omega HF, it is equal to omega H into 1 plus AM beta. That is a good thing. Now, what is the difference between omega H and omega HF? Omega H is the upper 3 dB frequency without feedback, omega HF is the upper 3 dB frequency with feedback. So, with the help of negative feedback, your upper 3 dB frequency, it is increased by the factor 1 plus AM beta. So, the bandwidth is enhanced. So, the point is that your upper 3 dB frequency is increased by the factor 1 plus AM beta. Omega H is the upper 3 dB without feedback, omega HF is the upper 3 dB frequency with feedback, fine. And the bandwidth of the amplifier, how we calculate it? It is FH minus FL. So, it is very clear that if we increase the value of FH and if we reduce the value of FL, then your bandwidth will increase. So, the negative feedback, it increases the value of FH and it decreases the value of FL by the factor 1 plus AM beta. Similarly, you can calculate for lower 3 dB frequency also, fine. So, your bandwidth is enhanced, and one more important thing is that you can see that the bandwidth is enhanced by the same factor by which the gain is reduced. So, your gain bandwidth product will be constant. You can understand with the help of this diagram, you can see that this black line, it is for open loop gain, gain without feedback, and when we apply the negative feedback, then you can see that although the gain is reduced for negative, by using negative feedback, the gain is reduced. Initially your gain was A, now your gain is AF, but your bandwidth is enhanced, So, we are getting the higher bandwidth with the reduction in the gain. Next property is interference reduction. Negative feedback, it can reduce the noise, it can reduce the interference. We can understand it. Suppose that we are having this amplifier whose gain is A1 and we have applied the input signal Vs here, and some noise, some interference is added, that is your Vn. Now, what is signal to interference ratio? It will be Vs upon Vn. This Vs upon Vn, suppose that if I say this is equation A, this equation A, it represents S by I ratio, signal to interference ratio for the amplifier without feedback. Now, with feedback, in the with feedback case, what we do? We add an additional amplifier before original amplifier. Your A1 is original amplifier, and to reduce the effect of interference and noise, we add an additional amplifier before this A1 to reduce the effect of noise, and this additional amplifier whose gain is A2, this amplifier, it should be noise free. So, the point is that to reduce the effect of interference by using negative feedback, we need an additional amplifier that should be connected before your original amplifier. Now, for the second circuit, just see what is V naught. We can calculate the value of V naught with the help of superposition. So, this V naught, it will be equal to as per superposition theorem, what we do? Firstly, we will remove, for example, if we remove this Vn source here, now what will be the value of V naught? Now, the value of V naught, it will be, now this A1 and A2 will be in cascade. So, V naught will be equal to A1 A2 upon 1 plus A1 A2 into beta. This is the first case, and of course, multiplied by Vs. Now, in the second case, as per superposition theorem, we will remove Vs. When we remove Vs and there will be Vn, in that case, in the feed forward there will be A1. So, it will be A1 upon 1 plus A1 A2 beta into Vn. So, to calculate the output voltage V naught here, we are using superposition. In superposition, firstly we are considering Vn source, then we are considering Vs source, and after that, as per superposition theorem, we are adding the output voltage getting we have got from these two cases, fine. Now, just again calculate the value of S by I. Now, this S by I you can see that it is Vs upon Vn into A2. Now, your signal to interference ratio, it is enhanced by the factor A2, and what is this A2? A2 is the gain of that additional amplifier which we have connected before the original amplifier. So, the point is that with the help of negative feedback, we can reduce the interference. If your signal to interference ratio it is increasing, it means that your interference is reducing, but the constraint is that to reduce the effect of interference, we need an additional amplifier that should be noise free, that should be interference free, and that should be connected before your original amplifier, and your S by I ratio it is enhancing by the factor A2. So, if we increase the value of A2, your S by I ratio it will enhance, it will increase, fine. So, there are 5 properties at the starting which I have discussed for negative feedback. Out of 5 properties in this class, I have discussed 3 properties, and the remaining 2 properties I will discuss in the next class. This is the reference. Thank you.